This is video 2 for the energy and power unit. Okay, so in the last video I showed you a table and it had various different things that have energy, and we compared them all to 1 gram of TNT. And we saw that chocolate chip cookies have more energy than TNT. And that's kind of hard to think about, because TNT is so explosive. So if I take a look at dynamite, which is TNT, and chocolate chip cookies, both of these store energy. It's chemical energy, and it's stored between the forces, or it's stored in the forces between their atoms. Think of it like energy stored inside a compressed spring. So when the dynamite explodes, the forces push the atoms apart at a very high speed, and that's like releasing a spring between the atoms. It pushes them apart. So if you think back to that table, the chocolate chip cookies have 8 times more energy than the same amount of TNT. Now, many people mistakenly then think that TNT will release more energy than the cookies. That's incorrect. If I were to take a cookie and catch it on fire, which we can do that, it would release the same amount of energy. In fact, it would release 8 times more energy than 1 gram of TNT. What is correct is that the dynamite, the TNT, will release its energy very, very fast, while the cookies will release their energy slower. And that leads us up to something called power. Power is how fast one form of energy becomes another. So the dynamite has less energy, but it has a higher power. It can convert its energy into heat faster than the cookies can. So the power formula equals energy divided by time. So notice, if one thing can convert its energy quicker, so that means it has a smaller time, like dynamite, it will have a higher power. So the shorter the time interval it is, the greater the power. The unit for power is the watt, and the watt equals a joule per second. So a joule per second is a watt. Notice also we can get energy out of here. See how the joule is equal to a watt times a second? So a watt second is a joule. That's a unit of energy. Okay, the next thing I want to talk with you about is batteries. These are devices that store energy just like the chemical bonds in a cookie. The chemical reaction in the battery causes the electrons to travel through wires attached to the battery. We call this flow of electrons electricity, and we'll come back to that later on this year. Now, a car battery contains 340 times less energy than an equal weight of gasoline. And that's very important when we go to talk about electric cars. Now, there's something else we need to discuss, and that's efficiency. A battery is 85% efficient. That means that 15% of that battery's energy is lost. 15% of that energy never makes it to the road. It never gets turned into kinetic energy, the kinetic energy of the car. Gas, on the other hand, a gas-powered car is only 20% efficient. So that means 80% of the energy in your gasoline is lost. It's not being used to get the car moving. So when we take this into account, the battery then is only 80 times, not 340 times less energy if we consider efficiency. Now it's looking a little better for the battery. So, we still get more bang for your buck for gasoline than batteries, but we can still make an argument to switch our cars over to battery power instead of gasoline power. However, we need to consider weight. A car will hold roughly 100 pounds of gas. And that will give the car a range of right around 300 miles. That's different for every make and model. Some cars are more efficient than others. But as a general rule, 100 pounds of gas will let you travel about 300 miles. Well, if I wish to travel 300 miles in an electric car, I would need a battery that weighs 8,000 pounds. That's a problem. One of the heavier vehicles out there, like a Chevy Suburban, weighs about 7,500 pounds. So take that car, add an extra 4 tons to it in batteries, just so that you can go the same amount. It's not going to work. So what we can do is we can start cutting this down. So what this means, if I had a 1,000 pound battery, that is 8 times less, I would go 300 divided by 8 miles. I don't have a calculator on me right now, but if you do that division, you can find out how far that car will travel. So as you can see, that's the real problem with a battery-powered car. We just don't have the technology yet to have a light battery which can have a very large range. They are getting better. I've heard of some cars getting up to 200 miles and they don't weigh a whole lot. But it's something that needs to be improved on before we can switch over to battery-powered cars. Another thing to consider is hydrogen. Hydrogen has 2.6 times more energy than gasoline. If I look at a gram of hydrogen and a gram of gasoline. So why don't we use hydrogen instead of gas? It'd make more sense. If you burn hydrogen, the product is just water vapor. You don't have to worry about carbon dioxide and everything else that comes with it. But unfortunately, there are several problems with this. First off, hydrogen is not very dense. Remember, density is mass divided by volume. So, in fact, hydrogen is roughly 10 times less dense than gas. So what that means is we need to store it as a compressed gas. So we need to take the gas, we need to increase its pressure. Now, when you compress it, you lose energy. So if we compress this gas, so if we take it and put it into a tank and keep shoving more and more hydrogen in it, we get a compressed gas. And that makes it 6 times less energy per gallon. Than gasoline. That's a real problem. Now it's not even worth it. Furthermore, when you have a compressed gas, you need to store it in a tank with very thick walls. So once again, we're running into a weight issue. So if we think about equivalence here, we get roughly 1 kilogram of hydrogen is roughly 1 gallon of gas. So because of these things, the hydrogen cars just haven't come about yet. And for a while, everyone was thinking that hydrogen would replace gasoline, but the physics of it just doesn't work out because compressing it, you lose energy, and you have to have a very, very heavy tank to store it all in. The nail in the coffin for hydrogen, you can't mine it. We can't dig a hole and pull hydrogen out of the ground. We have to get it from water, which requires energy. We pass electricity through water, breaking it up into the hydrogen and the oxygen. Or if we take methane gas with water in it, if we heat it to a very, very high temperature, the hydrogen is released, but that still produces carbon dioxide. So we have to be very, very careful about where we get our hydrogen. If we get it from methane, we're producing carbon dioxide, and that's the one thing we wanted to avoid to begin with. Uranium, I wanted to talk about uranium. So a good rule of thumb for a nuclear reaction is one we see for uranium-235. So in uranium-235, it's a fission process. We hit it with a neutron. The neutron gets absorbed. It turns into uranium-236. That's unstable. It splits apart into a couple daughter nuclei, releasing more neutrons and a lot of energy. And uranium-235 is used in a lot of things, from nuclear-powered subs to nuclear power plants to atomic bombs, weaponry. Roughly 20% of our electricity comes from uranium-235. Okay, cost of energy. This is where it really comes down to. This is really the reason why we haven't gone to a more environmentally friendly fuel. Suppose I wish to buy a calorie of energy, let's say to heat my house or to eat. What is the cheapest source? So if we ignore mining and the availability of it, let's say we have an infinite amount of stuff, and let's say it doesn't cost anything to mine, which we know that's not true, we can take a look at some things here. So here's some common sources of energy: coal, natural gas, gasoline, electricity, a car battery, a laptop, and a AAA. And when I say electricity, I mean from a power plant, such as one in Conesville. So coal costs $40 per ton. Now, if I were to look at it in terms of calories, for every 1,000 calories, it costs me 0.4 cents. That's cheap. If I wish to convert this into electricity, currently it costs me 1.2 cents. And again, that'll change, but as a rough average. Natural gas. We measure this with cubic feet. So it is $3 per 1,000 cubic feet. So a 1,000 cubic foot is a standard unit of measurement for that. 0.9 cents. We're not even to a penny yet. And then it costs 2.7 cents to turn it into electricity. Outside of Dresden here, we have a natural gas power plant that converts natural gas into electricity. The 2.7 cents, it's been a while since I've looked it up. It may be cheaper, maybe a little bit more, but it's relatively competitive with coal so far. Gasoline, the price jumps around. So let's just assume it's $2.50 per gallon. I know it's a little cheaper now, but it'll probably go back up to $2.50. So that means it's roughly 7 cents for a kilowatt, and it costs 21 cents to convert that into electricity. We talked about electricity. It's right now, it averages out to about 10 cents per kilowatt hour. So 10 cents here, and then obviously 10 cents if I convert electricity into electricity, it'd be the same. A car battery. Remember, these are lead acid batteries. I don't know if you've had to buy one recently. They're roughly $50 per battery. And that is a very cheap car battery. Last time I bought one, I think I spent closer to 100, 150. So that's about 21 cents for a kilowatt hour. And again, electricity is electricity, so 21 cents to make it into electricity. A laptop battery, again, it's been a while since I've looked up the prices here, but last time it was around $100 for a new battery. So that's $4. And then a AAA battery, as a general rule, it's right around $1.50 per AAA. So make this equivalent $1,000 for a kilowatt hour. And there's a very good reason why we don't use AAA batteries to power our homes. It would be way too expensive. Okay, so this first column then, the first one we need to focus on is the kilowatt hours. That's the middle column. This is the way we measure the energy in our homes. So the average home uses 1,000 kilowatt hours per month at an average cost of 10 cents per kilowatt. So notice the cost savings you have by heating your home with coal or natural gas. Not converting it, just burning it and doing this. In the 1950s, many homes were designed with radiant heating cables. You passed electricity through them, and then it would get hot, and that's how you heated your home. But to save money, many people started converting their furnaces into something else. That's what happened to me. My house was built in '55. It has radiant heating cables. I have since converted it over to propane because it's cheaper. So if alternate sources of energy production, such as wind, solar, and geothermal, are taken seriously, they need to be at least as cheap and as reliable as coal. And that is the real problem with some of these other forms of energy. They're just not there yet. They're just not cheap enough without government subsidies. Okay, real quick, some forms of energy. We have kinetic energy. This is the energy of motion. Potential is stored. Stored energy. Nuclear, this really should be nuclear potential energy, but it's energy released when you split an atom. Really, I should say when a nucleus splits. And then gravitational, this is energy released when objects fall. All right. I think we'll go ahead and stop the video right there.